Dear students, now let us take some of the problems from dual nature. This problem is taken from 2015 CET paper. It's like this. Find the de Broglie wavelength of an electron with kinetic energy of 120 electron volt. The options are 124 picometer, 112 picometer, 102 picometer and 95 picometer. Dear students, we all know that when a particle is moving, it behaves as a wave, and in this particular question, the moving particle is electron, and we are supposed to find out the wavelength of the electron, and what is the given data is the kinetic energy of the moving electron is given. So what do you get from this data? The de Broglie wavelength is given by lambda is equal to h by p. Lambda is equal to h by p, that is p is the p is momentum. P can be expressed in terms of kinetic energy. The formula is like this: lambda is equal to h by root of 2me, where E is the kinetic energy. Let me write the formula. The de Broglie wavelength lambda is h by root of 2me, where E is kinetic energy. In this problem, kinetic energy is given and we are supposed to find out lambda. It seems to be very simple, but as you proceed, you find the difficulty there. The idea is, what do we do for E here? Do we directly substitute that 120 in place of E? It's not that simple, because they are in different units. You have to convert the given data into appropriate units. Because in numerator, what do we have is, if you take h to be 6.6 into 10 power minus 24, it will be in joule units, and mass is 9.1 into 10 power minus 31 kg for an electron. And if you substitute these values, it will be complicated. So instead of writing this formula, let us make use of a ready-made formula in which we have already substituted for the values of h and m for an electron, and we came to a conclusion that lambda is equal to 12.27 divided by root of V. You know what is this V? It is the potential through which the electron is accelerated to attain a kinetic energy of E into V. You all know that for an electron, if V is the applied potential, it attains a kinetic energy which is E into V, from which this expression can be written as 2m. In place of E, I will write E into V under root. So how did I write this formula? By substituting these standard values for an electron. This can also be written in some other form, that is 150 by V whole under root. I repeat, lambda is equal to 150 by V whole under root. This is for an electron. Now here is the solution. Now to get the answer, you need to substitute for V, but how do you get the V? How do you get the value of V? What is 120 electron volt? It is the energy associated with the electron. How do you get the potential through which the electron is accelerated? We know an idea. Remember here, for an electron, if 1 volt is applied potential, then the electron acquires an energy 1 electron volt. I repeat, if the energy of an electron is 1 electron volt, it means that the electron is accelerated through a potential 1 volt. Then what do you get from the given question? It says that the energy of the electron is 120 electron volt. What does it mean? The electron is accelerated through a potential of 120. Now 120 is your potential given to the electron. So what I can directly get from the question is the value of V is 120 volt. So now I will substitute in my formula. Lambda is equal to, either you go for 150 by 120 or 12.27 by root 150. I think this is easier. So I will go to 150 by 120 under root is 5 by 4 under root. 5 by 4 under root is 1.25 under root. Remember, this lambda must be in angstrom units. So this will be in angstrom, this will be in angstrom. Let me say that that value is somewhere around 1.1 in angstrom units. So lambda is 1.1 angstrom unit, and all the options are in picometer. So when you convert this into picometer, this is somewhere around 110 picometer. I think the nearest answer is 112 picometer. So option B is the correct answer. The next problem is like this, dear students. Energy from the sun is received on earth at a rate of 2 calorie per centimeter square per minute. If average wavelength of solar light is taken to be 5500 angstrom units, then how many photons are received on earth per centimeter square per minute? Options are 1.5 into 10 power 13, B 2.9 into 10 power 13, C 2.3 into 10 power 19, and D 1.75 into 10 power 19. Dear students, this problem is based on the relation between energy emitted by photon and the number of photons. Do we have any relation between energy and number of photons? Of course, you must remember this formula, E is equal to NH nu. NH nu, very fundamental formula, where N denotes the number of photons emitted. But this has to be written in terms of wavelength, so I write E is equal to NHC by lambda. You all must be familiar with this. E is equal to NHC by lambda. In this, we are supposed to find out N. They have given you the energy along with the wavelength. Let me directly take the number of photons emitted as N is equal to E lambda divided by Hc. But how is E given? E is 2 calorie per centimeter square per minute. You can't substitute 2 directly there, because look at denominator. It is in joule units again, as we discussed in the previous problem. So you have to convert the energy into the joule system. I hope you are familiar with the relation between calorie and joule. 1 calorie is 4.2 joule. So this energy in calorie can be converted into joule units. But what about the per centimeter square per minute? Do we need to convert that into per meter square per second, which is the SI unit? You need not convert those, because the number of photons in the final answer should be expressed in terms of per centimeter square per minute itself. So you need not scratch your heads much, because you need not convert it into the SI units. So it's enough if you only convert the calorie into joule. That can be easily done. Then what about lambda? It is given, but dear students, as I have already explained in my synopsis part, you must remember the value of Hc. Every time you can't write 6.6 into 10 power minus 34 into 3 into 10 power 8 in CET. So I hope you will remember the value of Hc in 2 different units which I mentioned before. Okay, let me substitute all the values in SI for this particular problem. N is equal to, E is, it is 2 into 4.2, because 1 calorie is 4.2 joule. So it is 2 into 4.2. It is now converted into joule, and lambda is 5500 angstrom. How do I write 5500 angstrom? Is 5.5 into 10 power minus 7. I hope all of you followed this. And Hc, my ready-made value of Hc is 20 into, I hope you students remember this, it is 6.6 into 3, 19.875 approximately can be taken as 20 into 10 power minus 34, 10 power plus 8, it is 10 power minus 26, keep it as it is, 10 power minus 26. What is this? 8.4 into 5.5 approximately, I will take it as 9 into 5, can I write it as 45 approximately? I will write it as some 45 into 10 power minus 7 plus 10 power minus 26 is 19, 10 power plus 19 divided by 20, 45 by 20 is somewhere around What if I make it as 46 or it is 2.3 approximately? Do I have any options? Yes, in C I have an option called 2.3, but look at the power. Yes, the powers are also matching, so directly I come to a conclusion that it must be 2.3 into 10 power 19, because the other option containing 10 power 19 is way too far away from this approximate answer. So I'll go with C, which is the correct answer. Let's have a look at next problem. It's like this. The surface of a metal is illuminated with light of wavelength 400 nanometer. The kinetic energy of ejected electrons is found to be 1.68 electron volt. The work function of the metal is options: A 3.09 electron volt, B 1.42 electron volt, C 1.51 electron volt, and D 1.68 electron volt. Dear students, the most expected question from photoelectric effect will contain any two datas out of those three datas. You know what are those three datas? Number one, incident energy, number two, work function, and number three, maximum kinetic energy, because the Einstein's photoelectric equation is E is equal to phi plus k, work function plus maximum kinetic energy. Out of these three, they will give you any two. Look at the given problem. What are given? Wavelength is given, incident wavelength, that is incident energy is given. What else is given? The maximum kinetic energy k is given, and you are supposed to find out the value of phi. Let me write the expression for phi straight away. Work function is E minus k. So how do I write my E? You have to express it in terms of wavelength, so it is hc by lambda minus k. But you must remember the value of hc, as I am repeatedly telling you this. The value of hc can be written in two different units. One is in terms of electron volt, the other is in terms of joule. And also you have to consider the unit of lambda here. Usually lambda will be given in nanometer and kinetic energy will be in electron volt. So your hc should be expressed in terms of electron volt into nanometer. So remember, I'll tell you, the value of h is in joule second and the value of c will be in meter per second. When you multiply, you will get the unit of hc, which is in joule meter, but that doesn't serve the purpose here. You want hc to be expressed in electron volt nanometer. So the value of hc is 1240, as we all remember the value, divided by the wavelength is given to be 400 in nanometer. Remember, don't worry about the units here, because this is electron volt nanometer, this is nanometer, nanometers get cancelled, and you are left with electron volt value, which has to be subtracted by the k value, which is also in electron volt, 1.68. So further the problem seems to be simpler. This is almost 1200 by 400 is 3. Slightly greater than 3, it is 3.1. I hope you understood. This is 3.1 minus 1.68. 3.1 minus 1.7 approximately. So 1.7. So it is 1.4 approximately. Do we have any option? Yes. Look at B, which is very close to the correct answer. I think that itself is the correct answer. 1.42 in electron volt. Option B is correct answer. Students, I have taken one more problem from the same previous 2015 CET paper. It's like this. Light of two different frequencies whose photons have energies 1 electron volt and 2.5 electron volt respectively successively illuminate a metallic surface whose work function is 0.5 electron volt. Ratio of maximum speeds of emitted electrons will be options: A 1:1, B 1:2, C 1:4, and D 1:5. Dear students, in this problem, there is a single metallic surface and you are incidenting two different wavelengths on it, two different frequencies on it. Obviously, as the incident frequency changes, the maximum kinetic energy of the emitted photoelectrons will change, and you are asked to find out the ratio of maximum speeds of the photoelectrons in these two cases. So, how do you get maximum speed expression? Maximum speed is there inside the maximum kinetic energy expression. So, if you want velocity or the speed ratio, let us have a look at kinetic energy ratio. Let me write the expression for kinetic energy. K is equal to incident energy minus work function. Since we have two different incident energies, I have two different kinetic energies because work function is constant. So, what if I write K1 by K2 is straight away E1 minus phi divided by E2 minus phi. But what does K1 minus K1 by K2 give me? K is half mv square, K1 by K2 is V1 square by V2 square, because m is same in both the cases. So, this will give me the ratio of V1 square to V2 square. So, what is asked is V1 to V2 ratio, take the root of this. So, V1 by V2 is E1 minus phi by E2 minus phi under root. Incident energy in the first case is 1 electron volt, and in the second case it is 2.5 electron volt. So, it is 1 minus work function is constant 0.5 divided by it is 2.5 minus 0.5 under root is 0.5 by 2. 0.5 by 2 under root is 1 by 4 under root is 1:2. Option B is correct answer.